afternoon. Now, yesterday we had not a challenge, but we didn't finish the. I just said you find out, and I'm very sure that none of you bothered to find out the whatever. So we had the current being the same as integral z equal to 0 up to L, that is the length of the cylinder in the cylindrical quadratic table, and then integral from phi to equal to 0 up to 2 pi, and then we have the JR. So the ds, the Benon surface area in cylindrical coordinates, ds, is given by the R d phi. So this thread, you were reading for me the tau. Yes. On the identities, it is the taus which are there. The L, the tau, the L, the tau, the L. The surface, the Benon surface areas are not there on the, I think it is only the Cartesian coordinates where we know that the Benon surface area is dx dy. So then we multiply by R, phi d. So that's why the integrals we are opting for. This integral for, maybe I should say dz. We start with, I think, the inside one, when we are writing integrals. Yes. So if we are like if we have a triple integral, and this is x, y, z, then the inside one, we start with the inside one. So the one here will be the one we start with. For example, here now does it matter? Or we just need to know that we are doing this for this for that. So, but JR was equal to sigma V naught over R in V over A. Was this the case?
Yes.
Yes. Okay. So that means that we will have I being the same as integral z equal to 0 to L, integral phi equal to 0 up to 2 pi, then JR, which is sigma V naught over R natural log V over N, and then times the R phi z. This one would imply that our I is equal to, for z, we do the integral, it becomes integral in z, which is z 0 to L, which gives us L. For phi, it becomes integral in phi, which becomes phi from root 2 pi, which becomes 2 pi. Here we got a sigma, and of course these errors would have vanished a long time ago. And then we get being out of natural log B over N. But from Ohm's law, the resistance is the ratio of the potential across a conductor over the current that will be flowing in that conductor, which would be the same as V naught times the reciprocal of what we got there, which is natural log B over A over the 2 pi sigma L V naught. So the V naughts go, therefore R will be equal to the V naughts there. Okay, so this is natural log B over A over 2 pi sigma L. And if you happen to get this book, which is a collection of the lecture notes for the distance, it's exactly our notes on web, except that for it, it has more activities, objectives on each of the whatever, and then more examples, both worked examples and further examples. So far, we've this is how far we've moved in the book when you compare. Today I am starting on magnetostatics, which is magnetic fields in matter. And so we have covered all this, and we are left with all this. So it's not a big deal. It's mostly big because of some. So I also came with glyphs to make sure that I'm no longer trusting your efforts. So whenever I say get me this, some of you just want to make me fail. So now I carried my own book. And all should be well. Any question about the electrostatics and all that stuff? We now know the potential. You can solve the potential using the Brad operator dot divergence, dot Brad, the scalar potential, so that we get the Laplacian, which is equal to which when equal to 0 becomes Laplacian's equation, and this Laplacian's equation helps us a great deal to find out the potential for different types of configurations. And we got for the two electrodes which were infinite, and we were able to find the potential in between them. And then you got for the, so in your, I would like you to read about a spherical resistor. Okay? Yes. A spherical resistor whereby you have two concentric spheres and then you find out the resistance that these ones hold. If there are no questions about what we covered before, allow me take you marathon so that we finish magnetostatics today.
Yes.
And move on to maybe by the time we leave, we should have at least gotten an introduction to Maxwell's equation, so that when I'm probably meeting you online once in a while, you already know how things are moving. But once I introduce you to Maxwell's equations, you should be able to move on your own. So magnetostatics. In other words, these are magnetic fields in matter. Magnetostatics is the same as magnetic fields in matter. Or you can simply say magnetic field laws if you want. When we now look at the magnetic field lines, the magneto is for the magnetic fields, just the way we say electrostatics. So electrostatics, this is static charges, or static electric field lines. So magnetostatics is stationary magnetic fields in matter for this case. So that's why here we talk of the dielectrics, blah, blah, and remember, when we are looking at electric field lines, we are looking at how they are permitted in materials. When we talk about the magnetic fields, we look at how they are permeated, the permeability, which comes with the magnetization. So magnetization takes place first before these magnetic fields are permeable or are permeated. They are able to permeate through. So you have to know the basics of magnetization. That if you have a slab material like iron, call it a slab material because it is easy go, or easy come, easy go, then it means that when you put a magnetic material, for example, if I got a solenoid, and then inside this solenoid, a solenoid is any coil whose diameter whose length L, a coil whose length L equals, is greater than 10 times the diameter, where the diameter is this one here, qualifies to be called a solenoid. Any coil. So if I put iron in this coil here, if the current connected to this coil is in this direction, so it means that the current is coming like this, going down in these other parts, and if it is going down in these parts, if I was looking like this side would be looking like this, and if I'm looking from this side would be looking like this. But nevertheless, I could do that using the right-hand grip rule. So I could grab the wire, the solenoid, and make sure that my fingers are in the direction of the current, and the thumb will be the direction of the field, and we know that the field emerges from the side which is the north. Now for a non-magnetic, okay, when I say non-magnetic, I don't mean that when it doesn't, when a material is not magnetized, but when it is magnetic, like iron, is like when you are illiterate. When you are illiterate, you don't care. Like anything happens, you get feelings for anything. But when you get educated, for example, and you are knowledgeable, when people are talking, you don't get run around by emotions. You already know things. So you can't meet a lawyer and then intimidate him. If you say, I will kill you, you say, I will sue you. You get a point? When you are talking, when at the village level, for example, a teacher is known. You don't meet a teacher and then start talking of nonsense. He reasons you out because he is already oriented. But then when somebody is not educated, is not informed, he's just there. Anyone who talks, they bend towards that side. When this one talks about something, they are also like, what did you say? So that the magnetic dipoles in a magnetic material which is not magnetized are facing in all sorts of directions. Now when this happens, when you insert it in this solenoid and then you switch on, you tap the switch, then you get the current starting to flow and then the field lines start moving. And then you start getting all these magnetic dipoles for some time facing in the same direction. Aggregating the north where they are facing and leaving the other part being the south. When you take a lady out, for the guys, when you take a lady out many times, buy her fish, buy her wine, she starts getting oriented towards looking at you as somebody who can provide. And she may accept to be your wife in the future. If you promise that you'll never be broke, you'll always be giving her money. I don't know the ladies how you do it. is if you keep putting on nice braces every time, then you may let this guy look at you always, and you probably get interested in you at one time. This is basically for you understanding this, okay? These examples I'm giving you, just for you to understand this. So it is after, this is elementary, this is O level. This is, I think, S2, isn't it? Where you study magnets and P6. Magnetization. You can do magnetization by stroke. For example, whenever I'm repairing stuff, I would make sure that I go to the speaker of the radio, and from this speaker of this radio, I get the screwdriver, and then I start stroking. Put like this, and then when I'm picking the screws, I don't have to hustle. Just pick it, put there, I screw up. So that is one of the methods. Then there is induction. You get a nail, if you get this nail and you put another nail, and then you put a magnet, then all of them attract each other. That's basic knowledge. Once we have known this basic knowledge, then we start looking at a couple of other things. How would, if we wanted to diverge these magnetic field lines, what happens? When we have a conductor carrying current and it is having a field around it, and then we bring something around, how is this field behaving? Yes, sir. You want more clarification on how I came up with an S and N? Yes. Okay, I don't have a wire here, but I will use my fine art. So this wire, which you saw, comes like this from down, okay? And when once it reached here, I bent it. It went behind the other side, like this. So, and went on. So I will put the last one for purposes of you understanding. Today I want to demonstrate to you that when I tell you that fine art works miracles, then it does. So this is behind there, the other side. The wire is, this is coming, this one is going this side, and then comes out from the other side. So the current is flowing like this. So it will come and flow like that, flow like this, flow like this, go behind, underneath, and then come out. If I can just show you that this one is on top. Okay? So it comes out like this, goes here, goes here, goes here, goes underneath, and then comes out here. If I'm looking from this side, at this edge here of the coil, it's just because this thing is fake, but I could have it is fixed. Also, we spoil. This is what I'm talking about. This kind of nomenclature that it comes like this, then goes in there, make this solenoid. So if I keep a loop from this side, assuming I didn't make this bulb so high that they are the same line, then I'm seeing the current coming from here and going in a clockwise direction. So it is in a clockwise direction, so I put this other side. When I come this side, when I'm looking at the end of this, then I see the current coming like this, then unclockwise. And then unclockwise, this is the clock can't go this way and can never go this way. The clock goes this way. And so when I draw them artistically, this becomes the north, and this one becomes. And when I grab if I had grabbed this one like this, and this is the direction Is it okay? I do this because I know what matters is how you'll be explaining this stuff at the O-level stuff, O-level guys and A-level guys, not how you'll be chopping the car of B, because you're not going to use it down there unless you are going to do it at the postgraduate level. But you should be able to reach down there and bring out the stuff in their simplest way possible. So, like I say normally, our main aim is to lay a background towards the propagation of the Kasada. What is it again? I've explained. Again, in your mini meeting. Yeah? You have, I only have 2 hours with you. You have, you could even make it 12 hours with her. But only I have 2 hours here with you guys. So I'm just trying to make sure that if we could make it a little bit affordable. You can never, if I explain so nicely, everything can't flow nicely and you grab everything just here when I'm teaching. But you have a second chance. The video is always there. After the lecture, I normally put the video up. If you wanted to again see how I did it. 2, these guys are around, you guys are here. Like I said, I have only 2 hours with you, you have eternity with yourselves. I don't even know how you live after here. So, if you could give me these 2 hours, it would be nice. So we've already understood what happens when we diverge these electric fields. We know how or what happens when we curl these fields. And now we are trying to lay another background of what would happen if it is about the magnetic field. And then what will happen if we curl the magnetic. Once we have done this section of the course under magnetostatics, then we say, but these fields come from a current. And then this current, we looked at it under steady currents. How is this current produced? Then we shall look at electromagnetic induction. And then, fortunately, as we struggle to induce current, then we eventually get to be able to find that we can also, in a neighborhood, affect another coil. And then that was the birth of wireless communication, which is the basis of the mobile phone. And then from there we say, okay, we now know how all these things come about. We know the materials we can use. Then we start doing the actual thing of how the electromagnetic waves. At the end of this section here, we shall also lay down the boundary conditions. We got the boundary conditions for the E, and then the one which is the friend B. And here we could have said, since we need uniformity, this is electric field intensity, this is magnetic field intensity. And then all in all, this would be related to the magnetic flux density, whereby D is the same as epsilon E, where we get concerned more on how electric field lines are permitted in materials, dielectrics, and any other materials. And then this one, B, would equal to mu H, where we would be concerned on the permeability. How are these magnetic fields able to permeate in materials? And these materials, we need also to look at how are they susceptible to magnetic fields. So we looked at electric susceptibility when we were here. If we got a current, how is it susceptible to permit electric field lines? Then when we reach this other section here, we look at the magnetic susceptibility. How are these materials supposed to be or be able to have or to make sure that the magnetic fields can permeate? But we need to also remember a couple of things, especially from the prerequisite course, which was electricity and magnetism, where we said that the force on the charge Q, the force on a charge Q moving with velocity v, in a magnetic field of flux density, B is, we say this magnetic force is given by the Q in V cross. And what do we call this force here? Why are you calling it Lorentz force when it is a magnetic force? 2, we recall that magnetic force on a current conductor, the magnetic force on a current conductor, in a magnetic field, is this magnetic force on a current conductor will be the same as the integral over the closed curve IDN cross B, which you call the F is equal to BIL sine alpha, where sine alpha is the orientation of the conductor, then the L is the length, current, I is the current conductor, and where C so I want to make an online school, and I can employ some of you, those who are enthusiastic. Sooner or later, I want to make an online school, so I wanted to make sure it is an African school. So I will be getting people from Uganda, Nigeria, so they teach from there. And then people come and watch from the same place.
I want to be the head.
You have to pass through a postgraduate in education. But I am glad I have a headmaster now, and he qualifies because he has transformed. Yes, I want to say that Simbi has transformed from the time I met him. Now he's a transformed fella. Forget about the nature of the hair or whatever, but at least he attends on time, he comes on time, he attends fully, he has ditched the phone, the phone does not distract him these days anymore. So I have a head teacher. I think I'll make Fred the DOS. I'm starting with physics. Then I can extend later. So in a few years to come, people have to apply, and then I look at applications. And how I benefit, how people pay fees, I will tell you later in the future when you have understood what they call digital economics. So where this C here is a closed path, or a closed, since it is the path of the current, so we say closed, where C is a closed circuit. A closed circuit. The third reminder is the reminder about the Biot-Savart law. The Biot-Savart law, what some of you call the Biot and Savant. And the Biot-Savart law says that if we got a circuit that is during the current going through this circuit, and then we take the element of the circuit, and this element at one point or at some point away here, point P, we are likely to feel some magnetic field due to this current flowing through the so if this is the positive, this is negative, so our current will be moving in this direction. And then the couple of things, if this is our Benon, length of the wire making up the circuit, for example, or the current which is making up the circuit, then we will be able to have the, if this is the position vector from the element to the point where we are feeling a little bit of the magnetic field, and then this is the unit direction vector along the, from the element to the position P, and this is the closed circuit C. Ah, okay. I love that. The terminals. You state the reason why you are asking for excuse. You say you have misrepresented the field. Not just the terminals. So what? The terminals from like. So actually, I was hearing that the camera, the camera has a problem. So I must look at the camera like this. Anyway, I understand your dilemma. You sometimes want to keep your in a safe corner, but I'm the one who tells you, I won't be offended when you categorically tell me the mistake I've made. But don't try it. Don't try it elsewhere. You have to first we agree as a class. I have no problem when you say, excuse me, sir, on that line, that second line, that expression you have written this badly. The magnetic field of steady current, the magnetic field of the steady current, magnetic field of the steady current is given by Biot-Savart. Is given by the Biot-Savart law, and we say that the Biot-Savart law, the magnetic flux density experienced at B would be the same as mu naught over 4 pi integral over this closed curve C or circuit C, IDL cross R over R cubed. If you do the cross product, if you choose to use the roof, then you have to know that roof, this R of R magnitude gives you R roof. So that means you have borrowed an R from here. So if you have to, if you write it as the magnetic flux density at this point P, as integral over the closed curve. So if you have to use R roof by definition, or the unit direction vector along the R is the same as the vector, position vector, over the magnitude of the vector, which is the same as R over just simply R, since I am not going to be writing magnitudes. So this one would have taken one R from here in order to have IDL cross R roof. So below you get, I'm emphasizing this because when if it came out in a test or whatever, they say state bias var law, and then you find somebody choosing to use the other roof, and then he ends up with another cube below. So you need to know, when I use cross other roof, what would be the denominator. If it is other roof by definition is other vector over R. So if this one of other vector is over other cube, the other one would be, because one other would have been borrowed to partner with the other vector, other position vector, to make other roof. So you can't have other roof and then you have other cube below. Those of you who like programming, I don't want you to program us. I don't want you to program that. Another one. So when you reach exam or test and then you can't remember which one is the other group below. So at least you cram one, and you know I have an integral, see. So I have the I dl cross R vector, and then here you have R squared times R. So when you combine these two, then you get R roof. Or a curve, depends on where which one makes you a little bit happier. This is since the R vector is equal to R times R roof. Or you could say this and put those, but since we have this R adjustment, we put those values. Where the integration is being done along this curve here, which we got here, is along the integration is along the current path, is along the current path. Along the current path, or current, along the current, in the direction of flow. In the direction of flow, that means along the direction of the mu naught is the permeability of free space. It has a definite value. So mu naught equals to 4 pi times 10 to the power. Is it -7 on Rees per meter? And EDC. So what are the examples of, not examples, but what if we have a straight conductor being the one carrying our current? What if we have a coil which is carrying our current? I think you could also look at if you had like a disc, but for my purpose, I'll only take when I have a straight conductor, a straight current line conductor. A little bit, I take it as if it is infinite, and then we look at the amount of magnetic field that we will be able to feel around. And then we look at the circular coil, then we look at the the same case. So you can do a revision on the helix when you have the charges moving in a conductor. You look at revise these current turn conductors when they are having different currents, why they repair. When they are having same direction currents, why they got attracted to each other. That is the remainder. It's your business in your own, for your own consumption. For now, I'm just trying to lay a strategy of you being able to understand when I reach the point of propagation of the wave. So examples on calculation. Examples on calculation of magnetic flux density. Magnetic flux density. We start by getting an example one, whereby we look at the magnetic flux density. Magnetic flux density due to a current flowing, in a long straight wire, In other words, you have a long straight wire, and this long straight wire, if you take a little bit of an element of it around here, and then if we take this to be the, so if this is the x, if this is along the x, this being the L, and then we take this being along the y, and we take this element here. I've drawn it in a vague way to make it different from what we did in electricity and magnetism. So this is the straight conductor, and then this straight conductor with the current I flowing in it. If this is along the x and this is along the y, so we can do orientation just for purposes of knowing where we are. So if this is the x and this is the y, so this is the I and this is the j. So since we are interested in direction, so this is the indirection vector along the j, indirection vector along the I. Do we need to put dot when we are putting on I? I don't know. So if the current is flowing in this direction, then we can take the orientation of this, the line between the point P where we need to find the magnetic flux density, and take this one to be, since we have been able to write a bunch of phi's, let's take the angle there to be phi. Alafat. Are you taking notes? See that guy was he in first year or second year? Or he's still in transition? Remember, he picked when you were busy shouting, he picked that you write and remember. That's what he picked. So if this is the position vector R, yesterday I never wanted to talk about anything now because I wanted to make sure I finish my section. So I pretended I've never seen you so that I just make sure I finish the stuff. But I had a lot of stuff to talk about. So this is the, even today I want to make sure I finish a lot of stuff. So if this is the magnetic flux density and it is at an angle theta, then we can do a little bit of algebraic gymnastics. At the point flux density experienced is the same as mu naught I. We can put the I this side. Remember, it was IDL cross R whatever for 4 pi. And then, since we are still doing elemental, so we would have the dl cross the vector position. And then when we said if we use the vector, this one here, then we put there is an R cubed underneath. Or you can say that the elemental magnetic flux density is equal to mu naught I over 4 pi, and then you have dl cross R roof over R squared. Since just to remind ourselves, since R over R equals to, or you could say R roof equals to, R equals to R times R roof. Now, the dl, since we are moving along the x, we can have the dl being the, since along there is I, so if we go to the x and multiply it with the I roof, then we would be moving in the direction of dl. So then that means we can write this as dB, which is the same as mu naught I over, this is a constant, so 4 pi times 10 to the power negative 7, this is just current flowing through, it is not increasing or reducing, it's just flowing through the constant. And then so we got dx, I dx gives us the dl. And then that is being crossed with, so this would be I cross R roof. And then we divide by the R squared. So the dx, this one, this element here, since we are along the x, this element is equivalent to I dx. And because we have dl cross R roof, then we can have I roof cross R. And then this would imply that dB would be equal to mu naught I dx over 4 pi, and then magnitude of I roof is 1. Magnitude of R becomes R. And sorry, before I say becomes R. So I cross R gives what? R is along this, okay, this is, whether I put it along here, this is R roof, we have the I here, and then we are saying that here, we are having 1 times R magnitude, which is R, and then the sine of the angle between them. The angle between the x and R is how much? R is here. And which of course, when we reach here the direction, this is the position vector, but the direction is R roof. And then this is the I along here, if you compare with the relation here. So what is the angle between the I and the R? Fine. So this would be the same as sine phi, and so we have an R magnitude, and what is the magnitude of this R roof? 1. So this is 1 sine, but in which direction is it moving? And over R squared. Which direction is it moving now? Because whenever we cross 2 vectors, we get a new. So what is the vector when you have vector perpendicular to the I and J. Huh? This is I, this is J, which is according to orthogonality. What is the other vector? When we have I and K, I mean and J, then we get K.
I cross it.
So this would be along the. Now, we now have understood how the figure comes about, I mean how these values come about. And we can, sorry? Yes, R is moving down on this blackboard, assuming this is our plane, and the I is moving up according to the blackboard. Their cross product will be perpendicular to the blackboard. True or false? I is along the blackboard being our plane. Our roof is also along the blackboard, which is our plane. The cross product of these two will be perpendicular to the blackboard, which is also the same as this vector that will be perpendicular to the blackboard. From what you mentioned here, which comes out easily as the K. Who is it? He's closing the eyes like this, like he's trying to figure out how it's.
Then in the Bible server, this was R, this R. Then we do the Bible server.
Here.
No, in the previous year.
I made a mistake. That is history. I don't know what I had. You want to have that guy? Okay, but do you want to help him beyond this or what?
In the previous diagram, it's R vector and R vector and R.
In a different thing like this or what? Or this diagram like this?
Yes.
So what wrong did I do? I had this, and I had an R here, and then a P here, and then a dot, and then this should have been, oh, this is where I had an issue. But on where it is okay. Shirat, what is the R in the notes? So are you on Were or just on WhatsApp? Because I've been seeing you on the phone, so you should be able to clarify. In the notes, it's in the diagram. In the notes, it's okay. It has a roof here. I don't know whether we shall agree. I am careless because everything is on, and that's why I kept the videos unlisted. Unlisted meaning that you can watch them, you can share the link, and other people watch, but they are not open to the public. Because I have not removed the stories, I have not verified the content, and a few things that I write on board. But like I told you, those who came late, like I said, Fred, I appointed you as the director of studies for my online school. It is going to be an African online school, and the headmaster is Simbirone. He's the pioneer headmaster. And so we shall, I'm serious. When I dream, I put in action. The money is online, so I don't need a master. Maybe an accountant, I can get an accountant but not a master. So the idea will be that anyone can teach from wherever they are. If he is Spanish, he can teach. If he can speak good English that can be understood by Africans, he can teach from Spain. He films himself, uploads the video on our African school, and then our students benefit from that. It's he's in Karamoja, he can do his stuff and then still. So we want to make it a diverse school, classroom for all, and taught by everybody that can. There are people who want to teach, so those are the ones I want. So the analytics on the moderation online will be enough for me to, because I've done this since 2012, and now I feel like I just want to make sure I do it for. I believe there are many African universities who would benefit from my knowledge, because I'm the only African who has videos of classroom without preparing that I'm going to online, I want to make it thorough. No, come here, I do my stuff, and if you want to be part of it, you. And I haven't had anybody kind of comment in a bad way that you are fake or you don't know how to deliver. So I want to give other people also confidence to deliver their knowledge. I will never die. That's why I'm arrogant. These things will be there forever. There are people who have even saved them on their PCs. Even if YouTube is deleted, there are other websites who always make an image of YouTube videos, and they have them already on their websites. So I will teach until when I become a ghost again. You understand? And I am the only person with the two professors we lost, Professor Banda and, no, one. Professor Banda and then Kawa who retired. I'm the only one with their videos when they are teaching. One time I had started on my PhD, so they said you have to be taught. I said, okay, I will be nice, you teach me, but my deal was to make sure that I film them when they are teaching. So they taught me 2 courses until the end. I refused to do exams. So, but I had already gotten the video. So I have full videos of them teaching me. And I can easily show people how those 2 people used to teach, like, because they were the main senior people in our academy. No, they are for Professor Kawa, they are on YouTube. For Professor Banda, I put one on our Facebook page. Even your video of Saturdays on the physics page. I used to run the physics page, Facebook page, until when the president said Facebook is closed. And they closed Facebook because of me, but you don't know. I can explain. So, no, I can summarize. You people don't say that I brag, but I know. So, before the age limit in 2017, and massive. Before the 2017 age limit, I wrote an article on, I think, October 27th. And I think age limit climaxed in December. I wrote an article of how they are going to change the age limit and made a conclusion. And exactly how I wrote it is how events happen. But the other events which remained are coming on. So the story was too predictive. My conclusion is that the president may think that leadership can be transmitted sexually and include his family members. And then if we are not careful, we will end up like Somalia. And I'm sure that you already see the signs. That a whole command of army can threaten an American ambassador of an America which has killed, which killed Gaddafi, which killed Saddam, and a mere installed army commander can threaten such a country. when that country could kill Gaddafi, who had no debt. He had no international debt. We have 100 trillion in debt. Gaddafi was in surplus, producing oil. We haven't even touched any drop of oil. So I said, if we are not careful, we may end up like Somalia. That was the conclusion. But whatever I said happened. So they closed it because that's what the article was. I had also other articles. So when that happened, I never wrote again because I knew, even now I haven't written on Twitter since 2023 because I could have used that fella. And I could end up being like a Kwenza, being beaten everywhere. So I made sure that I keep myself busy on the Kali by Kali. Because even if he gets God to promote him, he cannot chop Kali by Kali. He can do whatever else he can do. So now, do you believe that they closed it because of me, or you still have doubts?
We believe.
Where can I get that article?
I can share it with you guys on Mwere. Just for you to believe. I wrote very nice, I gave scenarios. All scenarios happened, as I said, and this was on October 27th.
For me, it's not about believing, it's about reading the inside.
It's okay, it is online. So, back to the Kali by Kali. Using, I'm not going to have using the figure above. Using the figure above. Is it above or on the left extreme end of the board? Then we can find out that the tan phi equals to in terms of y and because the adjacent is x, because this is 180 minus. This is 180 minus phi, or pi minus phi, and that would be tan phi, tan phi over 1 plus, is it 1 plus or 1 minus? Tan phi, that is trigonometrical ratios. Back goes 2. Page. So this is minus y over x. This implies that x is equal to minus tan y tan phi. I did my stuff when I was in A level. I don't know about you. So the x, which we have here, we are trying, this is called using by change of variables, so you could say by change of variables. In the other part we say separation of variables. Here we use change of variables. So we want to move we moved from dl, so now we can make sure that we get this dx, and then we substitute in. So this means that the x is the same as? Yes. It is it? X was minus 1 equal to 5 instead of 10. Because we have been dividing. Yeah, point. It is 1 over the tan. This one comes here, point. Yeah, good. You are now. You are following. Yeah. So since you are, so this is cot phi, y cot phi. So dx would be the same as minus y. When you differentiate cot, you get. When you differentiate cot, you get what? So when you differentiate when you differentiate cot, you get minus differentiate a chord? Simon, what do you get when you differentiate a chord? Eh? My Lord. Okay, I can teach you. You can let, please, I'm now in charge. You can let Z equal to the cosine phi over sine, and let U equal to, and let V equal to, so Z is equal to, and then you use the quotient rule. And then whatever you get at the end of the day, it should be cos x squared phi, then this will be phi. So this is minus cos x squared phi. And I think it is, maybe as he had said, it becomes a minus because of the other cos on top. Since 1 over tan phi, I think I should have done that. 1 over tan phi equals to phi. This should have come here. The problem is not whether what you study is applicable. The problem is why you study it. Most of you would study it just to pass. And then when you pass, you erase your head. Pass and forget. And it gets worse when it is a semester system, where once you're done with the stuff, you just throw away your notes. Some guys throw away notes. Become free. So sine phi equals to, from the diagram, sine phi is opposite over, which is y, over the hypotenuse, which is r. So this is equal to y over r. Sine phi is equal to sine 180 minus phi. So the inside one is because sine 180 degrees minus phi is the same as sine 180 degrees cos phi. Then this would be minus cos 180 degrees sine. The sine n pi equals to 0. And then cos 180, you don't need a calc. You only just do this. You start from there. This is 90, 180. So this is negative 1. This is positive 1. And then you have this one as negative 1 in negative 1. And this one is sine phi, so this is positive. So sine 180 degrees minus phi equals to sine phi. So this angle here, in here, you just take this as the right angle triangle that you are applying the trigonometrical ratios or the Pythagoras theorem. So we have this one as 1 over r. So 1 over r would be the same as sine phi over y. But we need to find out, we already have the x, we need to find out the 1 over r squared. So this would imply that 1 over r squared equals to sine squared phi when you square both sides over the y squared. So I now have everything. I have utilized the diagram, so I can substitute in my expression for bio, then do the integration to get the total magnetic flux density, and and then I move on. So this implies that the male magnetic flux density, which was equal to this, now becomes mu naught I over 4 pi dx. Dx is y cosec squared phi d phi, and then sine phi, then sine squared phi over y squared. So I don't have much time, so this is over 4 pi times the sine squared phi over y squared for the 1 over r squared, then sine phi, and then we have the k root. And on summarize, on simplification, dB will be equal to mu naught I sine phi over 4 pi y. It is all of it is along the k direction. You have this y going with this bit of y. This is 1 over sine squared goes with this, so this is the only survivor in this. And when we do so our b on integration, integrating, will be mu naught I over 4 pi y, and then this is along the k, and we differentiate the sign. We integrate the sign, it is like differentiating a minus cos. And then we are having, I rubbed off the diagram, but this sine phi, this is our wire, this was the conductor, and this was the angle here, okay? And this angle phi, now this current here would have the field lines that are going everywhere until when you reach some point P. That whole layer of field lines at this point, if you want, in this line. So you have field lines. So the idea is that the moment you are able to look at this whole half of the field lines for this half, these same circles along this half within this region, they are the same lines which are on this other side, the same concentric circle. So you can't count them twice. So you can only take care of from, if you are moving, if this angle is moving in this direction, you go from 0 to 5. That's where we get these units here, 0 to 5. And then this one gives us B equaling to 2 mu naught. This is pi minus pi, no, minus 1, minus 1, minus, is it minus or plus the 1, which becomes 2. So 2 mu naught I over 4 pi y, and we are still moving along there. Therefore, this is the same thing we derived in electricity and magnetism, that the magnetic flux density is equal to mu naught I over 2 pi, the distance, the perpendicular distance, which was r by length, but this now is y. And this does so in the direction k. So you can revisit the electricity and magnetism exam methodology, also go to Nericon and look at, the Nericon is on Mwere, isn't it?
Yes.
And look at the scalar approach. Once you have looked at the two, you see whether you can get a little bit of sense of just trying to, the way it was drawn here was just to make sure that we make it look complicated. The higher you go, you see, when you grow and your English has improved, and like you are a lawyer, you start using terminologies which are very tough. Fragranto delito. Those things, so that you show that you are educated. Otherwise, you would keep it simple. Any questions so far? So if we had a coil, and that coil is the one we are going to use in the phone to make sure we can make a call, then we need to know how much field we can create to interact with the other coil, so that we can be able to induce a current in the other coil, and then that current be determined as a call. And then using the coding, if we can code our interaction, then make it a call, be able to pair time. You see, you guys will be slaves forever. We now buy phones that way. There's one thing that I want to really campaign. Microsoft cheats us. I told you already, I bought a laptop in 24, and this laptop had almost all facilities on it. Wi-Fi, infrared printing, etc. Even with the, so I don't remember the name, but it has a cable which really can transfer from a camera. I had a Panasonic camera by then to transfer the videos from a tape, like a small tape. But now the computer is obsolete. I can watch nice movies on it or whatever, but I can't put it on the internet because probably the next moment it will be affected by the virus. But the hardware is good. This laptop I normally come up with here when you are doing practicals is a Windows 10. It is not comparable to Windows 11. Windows 10 in 2025 will no longer be having updates. But my laptop, you can see, it is I think a project laptop they gave me because of using web. It is still looking good. But now they are going to make it trash. Why? I paid for it, it should work forever. Yeah, if I can look after it nicely, it should work. When I buy a vehicle, whether you say those of 90 watt, 98 or 97 are now obsolete, it is my vehicle, I paid for it, I will drive it until when it drops. It's a mechanical problem that will make it scrap, then I put it in a compound. But before then, you can't start telling me of nonsense of climate change, what emissions, that's your nonsense. The same should apply to Microsoft. So I want to get a good lawyer, and we sue Microsoft. Eh? The problem is that when you are buying a laptop, they say terms and conditions. And normally when we are installing on the PC, we don't normally read stuff. We say, I agree. So it's like how people apply for a loan and then they don't read the small things. And then when you find the things they were saying, if you default on this, you multiply by 10. Then they take your property. I don't get loans. I fear. I want to live a minimum life, humble life, put on my one shirt every day, and have no loan. I live large in my minimal whatever. So the second example, let's look at the coil. When we have a coil, and the reason we are looking at this coil is because of wireless communication. The reason we call this one a cellular phone is because once we shall see this more under electromagnetic induction when we are looking at Newman's formula. The moment we have our loop here and we get this current here, I1, changing, then it will produce a field, and this field will thread this other coil. And because when you change the current, the resultant field is also changing. The change in field causes a current I to flow. Now the reason we call this one a cellular phone, whether this is the spelling, is because of the word cell. We need the mast, like that one there. Those things you see on it are boosters of the network. Others are up there, I don't know whether they can be seen near the tank.
Yeah.
Now, because this field from this current cannot go far away, as we're going to see, for this coil. This coil here, I will put the words. But once I have this coil here, then away from its center, along the axis, we can feel some field there. But it's just within this range. So we would need to boost it. That's the reason we have a mast to boost my signal. Then it goes to a larger place. If you don't have a mast, then you don't have a network. That's when you start climbing a tree. Hello, school leader. Because you are out of the cell. That cell being provided by that mast there is yes, Muzaffar.
So how about this satellite phone? How does it work?
The satellite phone sends to the transponder of the satellite, and then the satellite sends to the potential receivers. That's why normally they say it is not tappable. The rebels like it because you use a particular friendly satellite that is able to serve you. So it goes the satellite straight, and then the satellite takes back to the different people.
How about the so-called pages?
You want to blow someone? So the two, I don't know. You can Google. You can Google how the pages work. But I think they have just been used of recent to blow up a couple of guys. I don't know whether they put it in. But even the lithium-ion battery is a potential bomb. Like it can explode if it is overloaded. So I don't know how they did it. Maybe they did it intentionally, that they supplied the ones which have the explosive. But even the phone itself is an explosive. That's why they say don't sleep with your phone on charge. Some of you will put the phone in the power and start surfing, and when you sleep like this, you put it will heat up with your mattress or your bed sheets, and before it could burn you up or blow up. And it may sound like, oh, don't call when the phone is in charge. And you are in charge and you are there. You are trying to align the electrons to charge up, and then you are calling, disorienting them. So the battery is busy disorienting, the charges are disoriented, oriented, and then it gets tired, it blows up. I think one of my phones, the one I use as a Wi-Fi hotspot, because it is always in power, and I'm using other gadgets to access that internet. Now it is developing a belly. Like when I hold it like this, I feel like it is protruding back and forth. So it is a so nowadays when it reaches 100, I remove until when I drain the 100. But I would just put it like a weekend. I reach home Friday, put it in power, and until the Monday, probably when I'm taking it off, coming up with it here. So now when I felt that bulging, now I remove it. When I check and it's 100, I remove until when because I refuse to buy MiFi, which uses no, there's one over there, but I refuse to use it because of the power. It uses, when you charge it, it does not even last for 30 minutes or an hour. And then you have, so that means you have to plug it in power. And then at one point, its battery will be like useless. The laptop I was talking about, its battery died. Because the time I spent in Norway, power only went once for an hour when our transformer in the neighborhood near the supermarket blew up. But they made sure everything is repaired within an hour. And for me, what I had done, I had gotten a paper and disconnected my battery, not knowing that that is dangerous. Because a battery should always be drained, charged. Drained, that's its purpose. Whether there is power or, when there is power, just unplug, use the battery. Once it says battery low, you charge it. Me, I said, why hustle? I'm on direct, no problem. Just put a paper, thought I was now conserving my battery to live forever. By then I was still dumb. Yes, because me, I'm a villager, I have gone to a place, I have this nice laptop, the battery is new, power is always on, so when I change and reach 100, I just put the paper and say, I'm keeping you. Now that battery cannot last for 30 minutes, or not even 15. If power goes like this, it also goes. Just you see it, you already warning you when power has gone. So we look at the magnetic flux density at a point along the axis of a circular coil of radius A and the distance x, and the distance x from the center of the coil, In electricity and magnetism, we just did find out so we took it like application of biosepar. But now we are doing it to show you that the moment we have a current flowing through such a coil of radius A, at some distance along the axis of this coil X, at some point P, we can feel some magnetic field there. Meaning that if we place another coil here and try to change the current that is flowing in this coil here, then it definitely will cause a current flow in the other, and that current can be used for any other purpose. You can use it for communication, you can use it for inducing something else, whether for remote control or for triggering a switch, and use it. But for the purposes of our course of a baseline for communication, that is telecommunication engineering, at that point we will be able to induce a current, so be able to communicate with these two coils. And then you always have like that mask there serving a cell, some cell, that cell which this government used to call those days that the cell, Mayumba Kumi. You have a cell, our cell, where you can easily communicate. These are people you can easily talk to, visit around. So that must will give some of us, the one at Sedat will give another group, the one at Crocodiles at CCE gives another group, the one up here gives, the ones in Mulago give, and then you are able to say network is good. Then when you go to my village, you move somewhere and there is no mask, so you can't have this field felt anywhere. And then you either climb a tree. Climbing a tree is to make sure that if there was an obstacle which was bending the waves to make sure they don't reach where you're going, in a space you study what they call malpath. And malpath is the idea that if you had a tree and then you had a GPS receiver then some of the waves of the satellite information, satellite signal can come and hit the tree, come to the GPS receiver. Another one can come straight to the GPS receiver. Another one can hit on the house, come to the GPS receiver. All of this will give you in analog TV, which you did not experience. Like I told you, we would have like 3 people reading news. It would be like juju. You have one who is clear, you have some other shape somewhere, until when you go on the antennas, and then you see the other 2 coming into this one, and then it becomes clear. So those other images were the example, for example, of the effects of mouthpass. But you are getting a signal, but which is not a value that is not the actual value. It had just been reflected from a tree. So that's why that GPS receiver, when we were installing it there, we made sure that it is clear that Mutuba tree had been cut completely. Just go again. And the only thing that was a bit higher than it was the lightning connector that was there. Otherwise, even it should be in a place where you wouldn't have any chance of a signal coming and, but of course, once a satellite has risen to a given height, you are sure that you'll be able to get. So at a particular time, at a particular navigation of the satellite, then it should be able to give you what is on the direct. Do you know how satellites work?
Yes.
When the data there is gotten by at least three satellites. When you have about 3 satellites, it's like having 3 people. If I close my eyes, let me see Kivayo and then Feima and Kauma. So if these were satellites and I'm a receiver, and then Kivayo says I am at the door to the staff quarters, I am moving at these meters per second, and I am, the time now is this. And Kauma also says the same, I'm in the middle of the lab, time is this, I'm moving at this speed. Fema says I'm towards the compound, I am at this, it is this time I'm moving at this speed. Then when I'm here, I am able to tell where I am. So comes the story when an old man was in the coaster. So one of the passengers says they were going to, I think they were going to Masaka, they were at Nsanji. So what they called the girl, and the girl said, hello, we are 227 in Namaojoro, but I will reach soon. So another man was called. He said, we are here Tabai Tababili. So the old man said, driver, where are we? Because one is saying they are in Namaojoro, which is dozens of dinner. And then another one is saying they are in Tabai Tababili. That is almost toward the Tebe airport. But they were in Sanji. So one old man said, driver, where are we? Driver, that's how satellites work. That the other, it is called triangulation. Is it triangulation or triangulation? Triangulation. Whatever it is. Yes. So once you have 3 satellites mentioning where they are, you can easily know where you are as a receiver. So you just need, when you have a GPS receiver, you only need 3 satellites that will tell you the velocity, their time and position, and then you will tell where you are. That's how GPS positioning works. So then we have an element here, and this, we shall take this to be the total, not total, but the main magnetic field experience. And then we shall have a dB prime here. And this dB prime here, we shall make sure it is at 90 degrees to the direction from the element here. So I don't know whether I should be able to get the nicer diagram to Griffith feared drawing this diagram. Just wanted to see whether I could find it in the book. I don't see it. So if this is alpha, and of course this is also the current direction going up, and this is the position vector R, this would be R roof. The X I have put, then what would be this angle here? If this is 90, this is alpha, the angle between the line from the element to the point P makes, what would be this angle here from geometry? It would be the same as this one. How is that this is this angle here, assuming we call this one angle beta. If this is angle beta, that means the alpha plus 90 degrees, this one here, plus beta. So this is also beta. So plus beta is equal to 180. And so this also here would be alpha plus 90 plus beta would be equal to 180 degrees. So if we find out the value of beta, which would be this one, then we would be having alpha plus beta plus 90 equals to 180. And then you find out, or you prove that this alpha is the same as. So from Biot-Savart law, then we have the this magnetic flux, then the felt at this point here will be the same as the mu Ri over 4 pi, and then you will have dl cross R roof. When we say R roof, what would be the denominator? And the elemento length, okay, the element of the coil which is around here. This element of the coil, when you look at the angle it makes with the line to the point where we need this angle here of the element and the line is how much? The element is here, my chalk, and then I have the line to the point P. The two meet at 90 degrees. So we state that dl and the unit direction vector, this one here, are perpendicular. And if they are perpendicular, their cross product would be sine 90. So this would imply that the dl we have crossed with the R roof would be equal to the dl, and then this is 1, and then sine of the angle between them, which is sine 90 degrees, and this is simply dl. So I got everything now. So I can do the as you like. Last case. So we substitute substitute, we need this because the component here, due to this element, is opposite to the component down due to this other element. So everything that would be on this vertical plane, we got one which is vertical upwards, then the one due to this one, okay, we'll have one up and down. Another one this way, there will be one in the one this way will be, so whatever is left is what would be along the X. If we took that to be the orientation, if this was the, for example, if this was I and this was J, but we're not gonna be bothered in that if that is the case. So if this is X, and we say that is along the X, we still get I. That is J. So the vertical components due to symmetry, they do what? They disappear. So we remain with the component of, the components giving us dB being the same as dB prime, and then we can take the we can take this to be Z roof. So that if that is Z roof, then Z roof. So let's keep this one out of this and keep this. But we can use the I instead of. I'm just going to make sure I keep with the notes, but we have left it as the I and the J. So assuming this is along the Z, okay, since we are using X as the distance, then this would be that Z. Of course, it would be the dB prime cos alpha. But also, if we say dB prime dot Z, that would be the same as dB prime. Then Z magnitude, which is 1. Then the cosine of the angle between them. The angle between the Z and the dB prime is alpha. So, which comes back to the same thing, collapsing the angle alpha. So, this means that we have dB being the same as the nu now I, substituting so the dl cross r became dl over 4 pi, and then dl, and then we have this culminating in cos alpha, and then we divide by the r squared. And r squared from the diagram is this one, which is the hypotenuse, which is this squared plus this squared. So we got this as a squared plus, since r squared equals to a squared plus x squared from Pythagoras, theorem. But we got a class which still can be gotten from the geometry of the diagram. Cos alpha, which is this one here, can be taken as the neighboring angle, which is the adjacent, over the hypotenuse, which is the same as the A over the hypotenuse, which is a squared plus x squared square root. So this implies that the total magnetic flux density is the same as, if you want, you can keep it that way, it will be the same as nu naught I, A, this A there, and then this combines with that to give us the 4 pi, this one here, a squared plus x squared, 3 over 2. And we are only having a, the only thing that is changing, I left my teaching aid in office, but the only changing thing are these elements as you move along the coil. And these elements are dl, so the only variable changing is this dl here. So it is from 0 until when we finish up the circular coil, which is the circumference, because it's already as A, Yeah.
I'm not getting it properly on when the L is perpendicular to R.
Okay. I can't bend like a circle. So this is the circle, okay, and this is the line which is hitting the circle. This is my coil here. The element is here. And this is the line that is coming from the P. And when it comes like this, if you just put the so if you put this line and shorten it, if you shorten this line to come and stop here, if you could shorten it slowly and make it like you want, because I could have started here as the point where I need the magnetic field. Then I keep increasing slowly to here, and maybe to infinity if I wanted to do some elongation. So that means it's coming from the radius of the circular coil, and radius of the coil meets the circumference at 9. So that's why we are saying that the element at this edge of if you took it as a tangent, that small tangent on the coil, then it meets that line at 9. That's why they are perpendicular.
Yes.
Okay, so then now this is just like gymnastics, and this would imply, and of course this we could put Z here. Roof, we don't have any problem doing that. Instead of putting it there, then some people say, how is this coming up like this? So B as a vector would be equal to mu naught. So the other one becomes 2 pi, then minus 0. So we have 2 pi mu naught I over 4 pi E nu A squared plus x squared 3 over 2, and it is along the Z if we write it as a vector. If we don't put this vector, then don't put Z roof inside. Because Z roof, I have left out there. This one here. This is Z squared. And then summarily, is it summarily? If we have, I don't think we need this anymore. Wow, managed to slow me down, and I can't finish this section. Do you have any lecture? Because people are almost playing.
Yeah.
We can go up to 7.
Why are we too straight?
We can go to 7. I'm going away, so if at the end of the day they say we have solved your problem, then how do I get? I told you my story in senior 2. When I did senior 3 actually, in my senior 3 first term, the guardian, we were a bunch of us who was supporting. So he would first collect enough money. And then you find the teachers chasing you from class. Where is your receipt? Not yet. And some of us were too emotional to start explaining. You know money is coming. So then when they did it twice, I went to the deputy. I said, "Do you know my guardian?" He said, "Yes." He struggles to get the money for last. And then they are chasing me, and he normally brings it in total, in full amount, and you never give me the balance after you have chased me from class. So he looked at me, a very tiny boy like this. He looked at me, then he got a paper, stamped on it, a cheat, and said, "Allow him 2 weeks." He said, "When it expires, you come for another one." So when I enjoyed that kind of privilege, that's when they changed the bishop at the cathedral, a school where I was studying. And then, because they brought a Muzungu bishop, after the quarrels that were within the cathedral, then they said if they are going to give a bursary, and they would call it that man's name. It was a Catholic school, me and a Protestant. I didn't care. I would say I would love this one. So they said if you get below 30 aggregates in O level, you will study A level for nothing. I said, you people, you don't know, you have just pushed a squatting person, someone who's squatting. So I just fall like that. So I fell my feet in a basin and read books. I chopped numbers and I got this. And they gave me a bursary and I did my PCM fine art for free. Then there was a very brown girl in S5 who started distracting me. And then I got low marks and the boss said, we shall cut off the... I dumped her and said, never talk to me again. No, she was not a girlfriend, but she would, I don't know, these ladies are funny. She would always pretend we have to discuss, you know, she had taken my focus. Me who used to look after boats when I was in O level, and I'm in A level, I'm like, and you know when you're on a bus, like now I was like the guy on the block. Now I'm losing time for my academics. So I dumped her, like I said, do your thing, I do my stuff. That's when I last paid fees in S4. Up to now I don't want to pay fees. And that's why I like giving things for free, because I don't feel like I should see you suffer, like, you should have things which are free. That's how it should be. So finally, I think this is just to simplify. We take away this, we take these two, therefore, this implies, since I am about to say something different, B would be equal to 2, so no, not that. So we have mu naught I A squared over 2 into A squared plus X squared, 3 over 2 Z. This is for one strand, for just one single loop of a coil. So for a coil of n turns, then we can have that B is equal to mu naught I. So mu naught Ni A squared over 2 into A squared plus X squared, 3 over 2 Z. And you can substitute for mu naught I pi A squared. If I have not, then you get magnetic moment and express it in that form if you want. So the radius and the distance, the farther away you are, and the huge, if it is huge, and it is far away, you are having a point far away, you can see they affect our magnetic field negatively. But of course up here, this other one, the radius now is good. The bit bigger it is, the more you have the... So in other words, if you are far away, then this one almost becomes negligible. Like it's like this one becomes very small, and then you can make some interpretations. But at the end of the day, that is not my concern. My concern is that with the coil, you are able to get a magnetic field at some point. And once if you can have a changing current in this coil, you can produce a changing magnetic field and induce some current at some point away from. What you can use it for is your own business. Okay? Now, when we have these, it is 5. So we shall look at the divergence of these magnetic field lines. If for example, the ones produced by current conductor, and see what happens when we diverge them. Then later on we see when we curl them, what happens. Of course, when you diverge them, when you diverge these concentric field lines, then you lose the field lines. You have managed to slow me down. First, you came late. Second, you... Anyhow, no problem. This is a good place to pause. So I am thinking that by Monday, Sunday, I worked on my garden, so I will be able to now mark this Independence Day. And if I don't mark, it is not you who tells me what to do. If I manage to mark this, then I will be. And we are doing, those of you who are doing instrumentation, enjoy your independence, because we will have our test on Thursday. So I should Monday, I should be able to come with the test. But if you feel it is not necessary to bring it early, since I can put the marks on where we first chop, so that by the time I go, we have chopped enough. I will tell you where I would have gone when I have gone. See you Thursday, those who come on Thursday, then the rest of you, see you Monday.